Good afternoon. My name is Pedro Firme. I'm from Tecgraf Institute of Pontifical Catholic University of Rio de Janeiro, Brazil. And our talk today is about salt geomechanics toward future natural gas strategic storage and well abandonment applications in Brazilian pre-salt. This is our agenda. We start with a brief introduction about the group I belong to, the Multiphysics Modeling and Simulation Group. Then we move for the content of the lecture properly with an introduction, some aspects on the multiphysical behavior of salt. Then it's followed by some applications to salt caverns, well stability, integrity, and well abandonment. And to conclude, we have some final remarks. The Multiphysics Modeling and Simulation Group is focused on the understanding, modeling, simulation, and prediction of several geomechanical problems and geomechanical related problems in geoenvironments. And we work with geomechanics, fluid flow, transport, geochemistry using sophisticated constitutive models and numerical methods for that, in special the finite element method, but we use other methods also. And our applications are typically focus on oil and gas problems, and also mining, construction, and software development in this context of geomechanics and coupled multiphysics, multiphysical behavior, multi-scale from basin scale to grain scale. This is, in a few words, this is the scope of the group. For today, we are focused on the well scale or fracture scale, some not neither reservoir nor grain, but by a centimeter or a few meters scale. So, moving to the topic of the lecture, hydrocarbon production triggers significant stress changes in the reservoir and surroundings, especially compaction, subsidence, and related problems. So there are field problems related to that, and this scenario can be even more adverse in case of karstified and naturally fractured carbonate reservoirs. So this is the case of the pre-salt reservoirs. These reservoirs have as cap rocks evaporitic formations and mainly salt rocks. Salt rocks present a meaningful creep behavior and very low, essentially no permeability. And they are useful as hydrocarbon barriers. This is let's say a sign or an evidence of hydrocarbons when we found salt in the lithology, but also in storage medium, geological repositories, and these capabilities, the creep and the very low permeability, make such rocks adequate candidates for geologic barriers in case of well abandonment. In addition to that, Brazil has hundreds of wells to be decommissioned in the next years, so there are challenges and opportunities considering well plug and abandonment, and also for hydrocarbon strategic storage. So let's see some aspects on the multiphysical behavior of salt. We observe four main physics: the mechanical, thermal, hydraulic, and chemical. And when we are talking about salt, we usually think salt creep. So we are talking about the mechanical behavior of salt. But this mechanical behavior depends on the thermal behavior also, because creep is thermally activated. So we have this coupled behavior, this thermomechanical behavior. Uh, and considering that we may have some repercussion on the hydraulic behavior when we are in a level of stresses and accumulated strains in which the volumetric strains are no longer negligible. So the rock undergoes dilatancy, microcracks open, and then these open microcracks um, become flow pathways for fluids, and with that we have percolation. With percolation, depending on the chemical compatibility between the salt grains and the percolating fluid, we may have reactive transport, the solution, and this is the way how the thermomechanical behavior relates in general lines relates to the hydraulic and the chemical behaviors. But for the scope of the lecture, we are focused on the creep behavior and eventually the role that temperature plays on the creep behavior. Uh, so, considering the thermomechanical behavior of salt, uh, our first observation is that mechanical behavior depends on deviatoric stresses, temperature, and time. So the constitutive models for creep need to consider stresses, temperature, and time. The expression you guys see in the slide describes how strain rates are usually formulated in salt, considering a thermomechanical behavior. We observe there is an instantaneous elastic contribution, there is an instantaneous thermal contribution, and a time-dependent contribution. This time-dependent contribution is exactly the creep contribution, and it depends on the constitutive model we are adopting to formulate or to quantify, predict the creep deformation. There are some constitutive models for creep available in literature and widely employed. Uh, you can see the performance of each of these models considering an experimental curve and how is the typical result of each of them. And for the applications here, we are considering the enhanced double mechanism with transient function. In the gray box, there are some references of papers prepared by members of the group on this topic. Considering dilatancy behavior, which is somehow crucial for the repercussion of the mechanical behavior on the hydraulic behavior, salt accumulates high creep strain levels before exhibiting microscopic failure. But if volumetric strains become relevant, the material undergoes dilatancy, and this is why controlling dilatancy is important. Once the salt undergoes dilatant behavior, there is the opening of the existent microcracks and likely the generation of other microcracks, and there is an interconnected pore network that is responsible for enhancing the permeability. So salt is no longer impermeable. So this is a problem considering salt as a medium with hydraulic isolation. So let's see some applications, starting by salt caverns. Firstly, there are some specifications that apply to all the models and the results and simulations presented in this lecture. We are adopting the finite element method using the commercial software Abacus, the enhanced double mechanism creep model, and either axisymmetric or 2D elements. We are not considering 3D analysis here, but in both cases, we are adopting quadratic finite elements, 80-node quadratic and quadrilateral elements. There are some capabilities which are not originally available in the software. Then we had to prepare Fortran subroutines to make them available. So we have prepared the EDMT creep model in a subroutine and a transient internal pressure to simulate the cavern construction and operation. These two functions, these two capabilities, we have coded and are using in Abacus. Considering this model of salt cavern, the goal is to evaluate the mechanical response of an offshore synthetic model of a salt cavern regarding salt creep, the latency, and stress paths during construction and operation periods. So we have a typical model considering a pre-salt lithology, and the cavern is open by solution mining, which is a dissolution process, but we are modeling it here using a mechanical transient pressure. It is a simplification of the process, but it seems to be working well. And we are simulating the construction and the operation periods of the cavern. Here we have a workflow to simulate the cavern construction. We are modeling the solution mining process using a mechanical equivalent approach. So we have a transient pressure scheme that simulates the cavern opening, while the transition between the transition from salt to brine by dissolution. So this gradient of the pressure changes in order to reflect this dissolution process. And then we have the brining and first filling processes, which represents the brine being removed from the cavern and being replaced with gas at maximum pressure and then at minimum pressure. So in a few words, this is a workflow for a numerical simulation of cavern construction by solution mining using mechanical pressures. And here we observe the stress changes provoked by this simplified solution mining representation of the cavern construction. In the end, we have a stress, a deviatoric stress of about 20 megapascal. So there is a perturbation. This is expected in field since we are unconfining a significant region in subsurface, and these deviatoric stresses are responsible for triggering the creep behavior of the cavern. Uh, One thing is important when we are simulating the cavern mechanical behavior is to controlling the internal pressures which are acting inside the cavern. So we have the internal pressures at the roof, at the halfway, and on the floor of the cavern. And we observe that as internal pressures decrease, deviatoric stresses increase. This is coherent, physically coherent. But what calls our attention is the strong decrease in the center plot of in the slide, and we have the maximum stress deviation, and this is critical for the mechanical integrity of the cavern. But we observe that these two boxes, the blue box and the green box, uh, are expressing how the internal pressures vary over the construction period of the cavern. And these internal pressures and the corresponding deviatoric stresses have to be checked uh, uh, with respect to plasticity envelopes or failure envelopes in general to for us to have an idea if the cavern integrity is kept during this period. After the cavern is ready to start operating, we have an annual operation cycle in the right plot that over a year the cavern remains at the minimum pressure most of the time, and there is an increase to the maximum pressure over 1 month and a decrease over another month. And this cycle applies annually over 50 years. This is the lifespan we are simulating here. Uh, we have the displacements, the evolution of the displacements of the strains and of the strain rates of the cavern. And these results are fundamental for us to control the mechanical integrity of the cavern. Considering well stability and integrity analysis, the goal is to predict the well closure by creep and compare these results with caliper logs for us to see if our constitutive models for creep are producing results which are validated uh, in relation to field results. So it's to for us to check our representativeness. So we have a typical pre-salt lithology involving salt and non-salt rocks, and we have an open hole interval, and we simulated the creep behavior, the well closure, and the deviatoric stresses, and we observed some problematic regions, observing the center plots, the center figures, where the well serviceability may be impaired if the well has these intervals of salt closure. So if these regions are prone to have stuck pipe or other kinds of operational problems. The regions between salt and non-salt layers, these interface regions are prone to slip. So these two pictures are expressing to us that we may have integrity problems in these interface zones prone to slip and serviceability problems in that regions where we observe a well closure in the salt layers. Comparing results of well closure, we are somehow in line with the field data. Here is some useful results for the industries, just to ensure that we keep a minimum drift for allowing casing to be run along the well. And here we have some problematic interface zones with these peaks in the factor of safety. So these zones need to be checked in terms of integrity. If we have slippage in these zones, we may have pathways for fluid leakage, and therefore we have problems in the hydraulic isolation of the well. And finally, we have well abandonment applications. Here, creep is not a problem, but on the other, but actually it is a solution for the closure of the well, thinking in a geologic barrier for the well abandonment. So we want the well closes by itself by the salt creep. So we have carried out some proof of concept analysis focusing on the well closure after the lifespan is reached. So we simulate the removal of the casing and the cement and leave the well free to creep and close the hole. We are considering a reference model and models where the creep behavior is stimulated by the pressure reduction inside the well and heating the well, because pressure reduction repercutes on the stresses, and temperature is another state variable important for the creep behavior. So we are trying to see how some stimulation methods are effective for us to have a quick well closure. Here we observe the times for the well closure if we don't use stimulation methods, the black curves, and we see this is really it's a slow process. But on the other hand, if we stimulate the well to accelerate creep using the pressure reduction in the blue curve, the heating the well in the green curve, and doing both of them, reducing pressure and heating the well in the red curves, we observe that we may accelerate this well closure, and then the well is spontaneously closed by creep. We observe that we are okay regarding the factor of safety. We are far from the latency envelope, so we don't have integrity problems over this closure period. And here we observe the evolution of the porosity and the permeability over time and over the mean stresses, because the geologic barrier needs to be mechanically sound, and also permeability and porosity have to evolve for negligible values. So in this way, we prove that we have the hydraulic isolation of the well using the material of the host rock of the well. So we have a chemical compatibility between the barrier and the host rock of the well. And this is the best case for an abandonment. So moving to the final remarks, this lecture has covered key aspects of the mechanical behavior of salt rocks of interest for engineering work such as caverns and wells. Salt properties such as creep and essentially null permeability are useful for casting competent hydrocarbon barriers and to be storage environments, and good for geologic barriers for well abandonment. On the other hand, creep deformation may be troublesome for serviceability and surrounding integrity of caverns and wells. Using salt as geologic barrier for abandonment, for well abandonment, is advantageous considering we have compatibility between materials, and we eliminate problems of compatibility between salt rock host formation and a cement plug, for instance. So thank you very much for the attention. If you are watching the recorded presentation, please feel free to send any questions or considerations by the emails shown in this slide. Thank you very much.